Welcome back. Today we are going to discuss the topic on non-linear pharmacokinetics. So phenytoin is one of the drugs which follows a saturable metabolism. It follows a non-linear pharmacokinetics. Okay, so here is a hypothetical data which we have for a similar drug similar to phenytoin, which is an anti-epileptic drug. So we have to find the required dose if the target steady state concentration is 10 mg per liter is necessary to yield a therapeutic response. Okay. So we have two data points here, concentration and dose. Dose of 160 milligrams yielded a concentration at steady state of 2 milligrams per liter, and dose of 360 milligrams had a concentration at steady state of 12 mg per liter. Before you watch this video, I strongly recommend you to watch my videos on one-compartment modeling, linear elimination, and also the Emax equation linearization and also Emax calculation. That's very important before you watch this video. Okay, why you have to watch it, I'll let you know in momentarily. So far you went through a linear pharmacokinetics. You know that dc or dt, the first video on my blog, one compartment model, is nothing but negative dc or dt is equal to minus kc. That is the amount of drug that is entering into the body is equal to the amount of the drug that is leaving out of the body via elimination process, right? But this is at a steady state. So here that means the difference of concentration with respect to the time at steady state is 0. If someone asks you, hey, what is the difference of concentration with respect to the time? At steady state it's 0. Why? Because there is not much change. Let's write the same equation for a non-linear pharmacokinetics. Here dc or dt is equal to, let's apply negative here, is equal to Vmax or Km plus C times C. Okay, so previously it's just a negative K. Now it's changed to a non-linear because it's a non-linear pharmacokinetics, because we are discussing about a phenytoin, a drug similar to phenytoin, which is having a saturable metabolism, right? Okay, now since this is a steady state concentration, so what is the amount that is entering into the body is equivalent to the amount that is leaving out of the body. So what is the amount that is entering? It is nothing but the dose, right? So we can call it as a daily dose that is entering into the body is equivalent to the amount that is leaving out of the body with this particular equation. Yes, so this is a non-linear equation. Okay, so now this equation we have to linearize to make more sense so that we can calculate Vmax and Km. So how do we do that? You have to watch this video that I posted earlier on Emax equation linearization, so you'll know better if you watch this. Anyway, I'm going to linearize it, this equation now. It is y is equal to mx plus b. In this format I'm going to write it. So y is nothing but dose or concentration d over c, and slope is nothing but a negative 1 over km. I mean, it's a negative slope anyway, so 1 over km negative, and x is nothing but the dose. Okay, dose plus b is the intercept, it's Vmax over km. Okay, it's b is Vmax over km. Now we're going to solve this momentarily. Okay, the first step in any calculation is this kind of linear equation is you have to find the slope, right? So let's find the slope now. Slope is delta y or delta x, and you know that is difference on y or difference in x. Our slope is negative 1 over km, as you're aware. Okay, now the concentration at steady state, we have 2, 12, 160, 360, right? Let's write that down. So concentrations at steady state is 2 and 12, and the dose is how much? It's 160 and 360. The first step is find out d over c, because our delta y is d over c of first point minus d over c of second point, you can say that, divided by d1 minus d2, right? So d over c, let's do that now. It's 160 divided by 2, that is 80, and 360 divided by 12, 12 3 is 36, 30. Okay, now the first step is slope, right? So 80 minus 30 divided by 160 minus 360. Okay, if you solve for this one, you'll have us, negative 1 over 4. Okay, so 1 over km, negative 1 over km is equal to negative 1 over 4. Then km is equal to what? It's 4. Do not do any mistake. Most of the students are doing the mistake over here. If someone asks you, hey, what is the km? Don't say 1 over 4, negative 1 over 4. Because negative 1 over 4 is equal to negative 1 over km. And km is equal to 4. Now that you know 4, the km, the next step is to find out Vmax. Let's do that. So daily dose is equal to Vmax times C over km plus C, right? So you have no idea about the Vmax, that's what we're doing. So let's take 2 points over here. Concentration at steady state of 2 and dose of 160 mg per liter. So it's 160 mg concentration of 2 mg per liter. Next time C over km plus C, and km is how much just now we calculated, 4, and concentration is 2. Vmax, that's what we're calculating. Okay, if you solve for this one, you'll have a Vmax value of 480. Okay, and the units for this are mg per day, and the units for km is mg per liter. Okay, now that we have Vmax, which is 480 mg per liter, and we also have km, which is how much? This is 480 mg per day, I'm sorry, and K is 4 mg per liter. Okay, that's what we have. Now, if someone asks us, hey, to achieve a concentration of steady state of 10 mg per liter, what is the dose that is required? That is, find the required dose. So what is the dose required? Let's do that. Now, we are going to use the same equation that we are going to use we used earlier. So daily dose, we have no idea. Vmax, we know that 480 mg per day divided by km, 4 mg per liter, plus concentration, that is 10 mg, right? Concentration at steady state that is required is 10 mg per liter, 10 mg per liter, times concentration at steady state, 10 mg per liter. Now, if you solve for this one, 480 times 10 divided by 4 plus 10, that is 14. If you solve for this equation, you'll get a value of approximately 342.86 mg per day. But as you're aware, is it possible for us to accurately weigh 342.86? Okay, as a pharmacist, what you're going to do, you're going to round it up to the nearest point. It's 350 mg per day. Alright, so I'm going to stop it here.